Hello everyone. This is a KTaNE tutorial for the module Reversed Boolean Network. This module does not require any edge work, so you can get right to it. However, before we do that, I first want to explain the basics of how regular Boolean network works. Because the two modules are very similar at their core, and understanding Boolean network will help you understand reversed Boolean network as well. So, if you already know how regular Boolean network works, feel free to skip to the timestamp in the description. Now, this is Boolean network. So on the module, there are 6 buttons colored red, green, or blue. And each of these buttons has either a black or white outline. And there's also a bunch of arrows connecting the buttons together. So, each of these buttons has a value assigned to it. Either 1 or 0. The starting value of each button is 1 if the outline is white, and 0 if it's black. The arrows represent that the value of the button the arrow points from is taken as input for the button it points to. So, for example, this button is an input for this button. And there's 2 types of arrows. A regular arrow, just like that, and an inverted arrow, like you see here, with this kind of perpendicular line at the end. And that arrow basically acts as a NOT gate, so it negates the input that the button receives. So if this has a value of 0, then the input becomes 1. And the colors of the buttons determine what condition those inputs must satisfy for the button to have a value of 1 in the next step. So, if a button is red, that means we have an AND gate, because all the inputs need to be 1. If it's green, then we have an OR gate, because the value is 1. At least one of the inputs is 1. And blue is a bit more complicated, because more than half of the inputs need to be 1. So, how exactly does that work? Well, each button can have anywhere between 1 and 5 inputs. So, let's analyze each of these cases. So, if there's just one input, that's just that input has to be true. If there's 2 inputs, there needs to be more than half of the inputs. Half is 1 input, so more than 1 input is 2 inputs. For 3, half of the inputs is 1.5, so more than that will have to be 2 inputs. Then for 4, more than 2 inputs is 3, and for 5, more than 2.5 is also 3. So, as you can see, if you have 1 and 2 inputs going into a blue button, that functions exactly the same as an AND gate. Because you need all the inputs to be true. And then for 3 inputs, you need 2 of them to be true at least. And for 4, and God forbid 5, you need 3. And that's where it gets pretty complicated, but we'll get there. How I like to note that down is as follows. So for A to be true, what needs to happen? Well, this is an OR gate, so we're going to have B or not D or E or not F. So I like to label these buttons from top, starting from top going clockwise, with the letters of the alphabet. So A, B, C, D, E, F, like that. So if this condition is satisfied, for the letters we substitute the values of the button in the step, then in the next step, this button will have a value of 1. That's how that works. And then B is going to be not E. C is going to be... green is another OR gate, so this is A or B. D is going to be F. E is going to be not C. And F is going to be not B. This is... yeah, I just write the condition for each one like this. So, what you do in a regular Boolean network is you take the starting configuration of values. So in this case, 0, 1, 1, 0, 1, 0. And you determine the values in the next step with these conditions. So, let's see. Is this condition true? Well, B is 1, so this is already enough for the OR to be true. So we have a 1. Then, not E is false because E was a 1. A or B is true because B was a 1. F is false, not C is false, not B is false. And we do that 2 more times, so 3 times in total. And then that final state we get after doing that 3 times is what we submit. That's a regular Boolean network, how it works. Now, reversed Boolean network. You can tell it apart from regular Boolean network by the fact that the status light is in the bottom left as opposed to top right, and by the fact that some of the buttons can have a gray outline rather than white or black. Like the module name suggests, for this module we're basically reversing the process of solving regular Boolean network. So, rather than getting the starting state and figuring out what the final state will be, we're given a final state and we have to figure out all the possible starting states that lead to that specific final state. And after we've done that, we then need to find out, for each of the buttons, how many of those starting states assign that button a value of 1. And then we rank the buttons based on those total amounts of states and press them in ascending order. So, just as a hypothetical example, let's say we only have 3 possible starting states, and those are 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, and 0, 0, 0, 1, 0, 1. So, this button, the first button has a value of 1 in 2 of these states, and then the next one in 1 state, then 0, then 2, then 2, then 3. If there's a tie, you can press the buttons with the tied count in any order. So we would press the third button, then the second, then in any order the first, fourth, and fifth, and then finally the 6th. Also, those gray outlines, which were not present on Boolean network, mean that the state of the buttons is unknown. So we could have a 1 or a 0 there, and it would be valid either way. So, again, what I like to do is just write the condition for each button as a logic statement. So like this. A is true if E was true, B is A or D. Or no, sorry, A and D. That's a blue, not a green. I was looking at the green that goes into it. And then C is not A and not B. D is A and F. Oops, so I did the same thing again. A or F, because it's green. E is C, and F is not A. Also, I like to do the same thing with the negative conditions. So what it takes for the button to have a value of 0. Basically, I just invert all these conditions. So if there's just one input, it's as simple as just negating the input, or unnegating it if it's already negated, like so. And for the ands and the ors, there's something known as De Morgan's laws, which say that if you have a negation of an A or B, that is equivalent to a not A and not B. And likewise, if you have a negation of A and B, that is the same as not A or not B. And this generalizes to however many inputs you have. So same thing with A and B and C. Negating that would give us not A or, not B or, not C. You just negate all the inputs and then flip between and or. An intuitive way to understand this would be, I guess, because an and requires everything to be true, if only one thing is false, that's already enough for everything to fall apart. And that's exactly what an or checks for, if only one thing is true, if at least one thing is true. So, to negate A and D, we're gonna have not A or not D. Negate not A and not B, we're gonna have A or B. And to negate A or F, we're gonna have not A and not F. And then, once we have that, I just get the buttons values, the ones we know at least. So like this. So B is false in the final step, so we have not B. And then we also have D is true, E, and F. And then I like to put the number 3 to indicate that this is the value in the third step, because we're working backwards from step 3 to step 0. Now, we can start substituting. Because what all this means is basically, for this button to be true, or false in this case, for this button to be true in the current step, this condition has to be true in the previous step. So for not B to be true in step 3, this needs to be true in step 2. So I just replace it like that. And then D, same thing. becomes that, E3 becomes C2, F3 becomes not A2. And now, oh yeah, by the way, I recommend putting ORs in parentheses, because if you don't, it can be ambiguous if this OR means like A2 or F2, or if it means A2 or F2 and C2 and not A2. That kind of thing. So yeah, this just prevents confusion and ambiguities. So now we can simplify this a bit, because notice how we have this not A2 here. This not A2 is always gonna be true by default. This OR is always gonna be satisfied by default because of this not A2 being true. So we can just get rid of it, because it doesn't really restrict anything. And then for this A2, because this not A2 is true, A2 is gonna be false. So for this OR to be true, this must be true. So this just becomes F2 on its own. And we keep going like that. So F2 becomes not A1. C2 becomes this. For ANDs, you don't really need the parentheses because it's all ANDs in here. And the most outer layer of this. So whether you do this or this, doesn't matter. It's like doing 2 plus 3 plus 4 or 2 plus 3 plus 4. And then not A2 becomes not E1. But this not A1 and not A1, we can just simplify it to be not A1. And then one last time, not A becomes not E, not B becomes this. It's an OR, so you put it in parentheses. And then not E becomes not C. And now, we've substituted everything down to the starting step, and we're left with an OR. And we don't like ORs, because we don't really know what happens with ORs, because we can have 1, 1, 1, 0, or 0, 1. So we can't tell for sure that any of the buttons is true or false. So what I do in this case is I split it into 2 subcategories. Either A is true and this, or not A is true and this. And notice how these 2 subcategories don't have any overlap, because this has A and this has not A. So if there were to be an overlap, it would have to have both at the same time, which is a contradiction. And also, these 2 cases add up to this. So no matter which case that satisfies this we pick, is going to fall into exactly one of these subcategories. So the total number of cases is going to stay the same. And now, because we've split it like this, we can simplify. So this not A guarantees that this OR is satisfied, so we can get rid of this. And this A being true means this not A is false, so this OR has to have the not B in it. And now I write out each of the subcategories that we've made like so. So if the button is true, then I write a 1. If the button is false, then I write a 0. Otherwise, I write a dot. So like 1 dot 0 0 0 dot, and then 0 dot 0 dot 0 dot. And now, each of these subcategories represents 2 to the n possibilities, where n is the number of dots. So 1 dot means 2 possibilities, 2 dots mean 4, 3 dots mean 8, and so on. Because there's 2 ways to fill each of these dots, and the dots are independent of one another. And also, each of the buttons represented as dots is going to be true in exactly half of these states. So for a button marked with 1, the number of states in which it's going to have a value of 1 is just the total number of states this covers. So we have 2 dots, that's 4 states. And then for a dot, it's half of that, so 2 states. And then these are never going to be 1s in this case, so that's 0, 0, 0, and then 2 again. And then for this one, we have 2 to the 3, because 3 dots, so 8 total states covered by this. And Here we have 0, and then half of 8 is 4. So 0, 4, 0, 4. And now we just add these up. So we get 4. 2 plus 4 is 6. 0, 4, 0, 6. So we press the third and the fifth button, then the first and the fourth, and then the second and the sixth. Just like that. Now this is what I would consider kind of an easy case of this module. A harder case is something like this, for example. One of the reasons why is because you can see we have a blue button that has 3 inputs going into it. Scary. So for 3 input blue buttons, we need at least 2 of the inputs to be true. So I just write this as 2 of, in this case, C and not D and not F. For B, we have A and C. For C, we have not... Oh, no, sorry, I was looking at D. For C, we have not F. For D, we have not B. For E, we have not A or not D. And then for F, we have not E. A lot of nots. And then we negate these like before. So, these, we just remove the negation here. Not A or not D negated becomes A and B. And C negated becomes not A or not C. Now, how do we negate this? Well, because 2 or more of these being true means this whole thing is true. 1 or less of these being true means the thing is false. And 1 of less of these being true translates to two or more of these being false. So we can just negate these in this case, and that does it. This only works that way for if we have 3 inputs, because if we have 4 inputs, for example, let's say we have, well, a 4 input requires more than 2 to be true, so at least 3. So let's say we have A and B and C and D, and we need at least 3 of these to be true. Well, 3 or more mean this is true, so 2 or less mean this is false. So if 2 or less are true, that means 2 or more are false. So this becomes 2 of the negations of these. That's how you can do that. So basically, this number just becomes the minimum number of falses that ruins this. Now, let's get the final state of the buttons. This is gonna be not B and C and D and E. 3's everywhere. And now we start substituting. So not B becomes this, not A2 and C2. C3 becomes this. E3 becomes this. E3 becomes this. And now we already have a bit of a complicated situation because there's 2 ORs. And we don't have anything to simplify them outside. So, as much as I like to avoid splitting early, I feel like in this case it will have to be done. There's going to be more substituting and simplifying later, but we don't want things to get too out of control, because if you get like a spaghetti sentence with 10 or more conditions, then things are going to get messy. So I'll just do A2 and then not A2 and like that. And now we can simplify this a bit. So A2 here means this OR needs the not C2 because this is going to be false. And the same is true for this OR. That needs the not D2. And here the not A2 makes these ORs satisfied by default, so we can just get rid of them. Now, let's continue with the simplifying. Now we have 2 that we need to get down from step 2 to step 0, but the process is the same. And again, these are mutually exclusive because this has A2 and this has not A2. So, A2 becomes this in the first step. I'm gonna make this wider because this is probably not gonna fit. Not C becomes this. Not F becomes this. Not B becomes this. And not D becomes this. So, we can simplify this because this F1 means this dot F1 is false. So, we need two of these to be true, but this is already false. So, we absolutely need these two to be true now. So, this just becomes an AND gate because we need two of these to be true anyway. So, that's how we simplify those. And now because this C1 is here, the not C1 is false, so this OR has to have the not A1 to be satisfied. Now for the second one, not A becomes this in the first step. Not F becomes this, and not B becomes this. Now I'm gonna actually wait with splitting this for now. Let's take a look at this first. So C becomes this in the 0 step, then not D becomes this, F becomes this, E becomes this, not A becomes this, and B becomes this. And you might notice something right now. So we need two of these at least to be true. However, because C is true, not C is false. And because not F is true, F is false. So we already can only have one true here, which means that this is actually a contradiction and cannot be true ever. None of these cases match. None of the possible cases match this subcategory. So we can just delete it like that. I just realized I forgot to put ones here, whatever. So now we just take care of this. And I'm not gonna split it yet. I'm just gonna wait for now. Actually, no, I'm gonna split it because these both have not C1, so let's go. Not C, or C1 and then not C1 and. So, this C1 means not C1 is false, so this OR has to be then not A1. Be satisfied? And then this C1 again being true means this is false. So this is still that what I deleted has a value of 0, so we still need two more here. So this just becomes an AND gate now. And then for this case, the not C1 means this OR is satisfied by default. And in this case, this not C1 inside this 2of thing has a value of 1. So we only need one more of these to be true. So I'm going to remove this and make this a 1of, which is really just an OR gate. Because if we only need one of these to be true, then we have freedom of choice here. And again, I'm not going to split this yet. Let's just keep simplifying or working backwards. So C1 is going to be this, D1 is going to be this, F1 is going to be this, E1 is going to be this, and not A1 is going to be this. And again, not F being true means this is false. So we need both of these to be on, so this is an AND gate. And now, because D is true, not D is false, so we need the not A in the OR. And we don't have any contradictions there this time. Now for this other statement here, not C becomes F. This becomes that. By the way, if you ever have like nested ORs, well, let's say this was E1 for example, then if you have something like this, for example, then because this is OR, you can just lift these parentheses. But we don't have an E in this case. We have an F. So that just becomes not E. And then okay, here we have another OR. And this is not nice here because we have two ORs, and not only do neither of them get resolved with what we have, but also they have nothing in common, so we can't do the simple splitting trick, we'll actually have to split this twice. So, first we split the one with the not A, so we go A and not A and. Of course, the order in which you split these doesn't really matter. So, in this case, not A satisfies this OR, so we can get rid of it. In this case, the A means this is false, so this has to be true. And then again, we'll need two cases, and for each of these, we'll have 2 of these cases. So we'll have a total of 4 cases. 2 where B is true, 2 where B is false. So we'll do B and, not B and, not B and we'll mix and match like this. First case goes here, second case goes here, first case goes here, second case goes here. So you can see you have B and first case, B and second case, not B and first case, not B and second case, just like that. And now we simplify all these. So not B means these ORs are going to be satisfied by default. And these Bs means these ORs have to have not E to be satisfied. Like that. And now we're done with the simplifications, and we have 5 independent cases. Yay. You can see, like, here B and A, B and not A, not B and A, not B and not A, so these are all independent from each other. And they're also independent from this, because this has not F and all of these have F. Just if you wanted some... How do you say assured as a noun? You get the point. I guess the word I was looking for is affirmation here or something. So here we just do the same thing with these. So 0, 0, 0, 1, 0, 0. Nothing special there. That's just going to be exactly what you think it is. Only one case there. So 1, 1, any 0, 0, 1, 0, 1, any 0, 1, 1, 0, any 0, any 1, 0, 0, any 1. Now here we have one case, so that's just going to be 0, 0, 0, 1, 0, 0. Simple enough. Here we have 2 cases, so we're going to have 2, 2, then half of 2 is 1, 0, 0, and then 2 again. We have 2 dots, so 4 cases, 0, 4, 2, 2, 0, 4. We have 4 cases again, 4, 0, 2, 0, 2, 4. Here we have 8 cases. So 0, 0, then half of 8 is 4, 4, 4, and then all 8. So, time to sum up. 6, 6, 9, 7, 6, 18. So we press the first, second, and fifth button. Then the fourth, then the third, then the sixth. Just like that. And that's reverse Boolean network. At least my method for it. So, yeah. The hard part about this module is just coming up with a method that works and doesn't take forever. Because, I mean, in theory, you could just analyze all 64 possible states one by one, but, like, have fun doing that. I do not recommend that at all. Not like I tried. Because I just knew that would be miserable. So, that's it for the tutorial. Thank you for watching. Hopefully you found it helpful, and see you next time.